All right, so we're looking at this. If we could make this less than, oh, sorry, Amanda.
All right.
All right. Why don't we start out with this? This will be even better. Let's start out with okay. Now, what I'm going to do, yeah, this is fine. That's fine, as it is. This thing, I'm going to add and subtract this. Looks like you see where I'm going with this? I don't have enough paper, but here, I'll try the pen thing. Maybe it'll be better this time. So I'm going to have the integral f d alpha plus integral g d alpha plus the sum over, let's let p be the joint refinement of p1 and p2. And I'm going to have f of xk plus g of xk bracket delta alpha k minus exactly the same thing. So, cross such amongst minus integral a b f plus g d alpha close bracket. Okay, so all I've done is add and subtract this term. Okay, now what's the standard operating procedure? Yeah, I'm going to take these two with this, and this with that, and write this thing then is dominated by integral from a to b, f d alpha plus integral from a to b, g d alpha minus the sum over the refinement, the joint refinement of f of x alpha plus g of x. Now this is k, I'm sorry, g of x k. Delta alpha sub k, yes, all that's true. Close, add another one. This is the triangle inequality. And then here, let me turn this around. So we have the integrals first. And then we take this thing away. And it's the same thing. So let's see if I can write that successfully. So that's after splitting the absolute value in the earlier step into two pieces, having added and subtracted and so on. Now, the sum, we don't know about the additivity in the integral, but we sure know about additivities and sums, right? We can take this sum apart and leave this one together. We can leave this one together. Well, this partition has a norm finer than delta. So if I take this piece with this guy and this piece with this guy, each one of those will be an epsilon over 2. Here's that. So I have an epsilon over 2 there. I'm trying to control this. And You know what I have to assume? I'm trying to not assume this, but apparently I have to. I can certainly split this sum up the way I said with yet another triangle inequality. They can have the f's minus and the g's together, right? Each one of those would be less than epsilon over 2. So this piece up here is going to be small. Who says this piece is small unless we make an assumption? And it's a natural assumption, right? You have to assume that f plus g is still just integral with respect to alpha. Just assuming that it's integral doesn't mean it's linear, but in order for this thing to be legitimate, it has to be integral, which means that there's a third partition. So this is going to be within epsilon over 3. So this will be epsilon over 3, epsilon over 3, epsilon over 3, less than epsilon. But that shows that this is true and this is linearity. I was trying to avoid having to assume. Separately, I'm sure we can prove that if f is integrable and g is integrable, then f plus g is integrable. Right? That's not what we showed here. We showed how to get it once you know it is. So we would have, had we proved that first, we would have said, well, f plus g is still integral with respect to alpha, so that this difference could be controllably small, that is to say, less than epsilon over 3, right? And then epsilon over 3, epsilon over 3, epsilon over 3. Yes, sir? Yeah, well, how would you do that? The linearity or the existence of f plus g is agreed.
I was just thinking about linearity. Is this the definition of statistics?
No, this isn't.
I would like to use that definition.
Well, I use the definition that for sufficiently fine partition, the Steel's sum with that partition is arbitrarily close to the limit. Because I knew about sums and differences and limits. Limits are linear. You know, the limit of ax plus b is a times the limit is whatever x is doing plus b. Right? So I knew that going in, and I thought that would be, I mean, we did prove it. We did prove it. And separately, we could show that f plus or minus g is really still just integral if f and g separately are. And there, I think the soup and int thing would be, but you would have to use the statements like this, that the soup of f plus g is less than or equal to the soup of f plus the soup of g. Int, right? Whenever you get into soups and ints and you start not just adding them, but if you subtract them, there's a whole mess of little identities that you have to know. You know, like what's the soup of f minus the int from g in terms of f minus g? Is that always greater than or less than the soup of f minus g? There's a bazillion, right? It's the soup and int applied to linear expressions. We'd like to know if I have soup of f, certainly the soup of f plus the soup of g is greater than or equal to the soup of f plus g. But you have to prove something. There's a whole wrap. You know, if you have two things, you can have plus or minus, you can have soup or int and even position. So there's a whole bunch of those things that you need to prove. So I try to stay away from those if I can, and that's why I went this direction. But you might be able to do that. How would you start? If you want to show, you would have to show for some partition that the soup minus the int for f plus g times the delta alpha summed up over the partition is less than a preassigned epsilon.